So, hi. Hey everyone, welcome all to BuildML's second research Hangouts. The first one was sort of open and efficient foundation, essentially Llama, open and efficient foundation language models. This time we're gonna take a crack at recommender systems, and this paper sort of calls into question a bit of sorry, one more person joined. Yeah, a bit of I would say maybe a hot debate in recommender systems, primarily around what models should be considered SOTA, and how they should be evaluated. So quickly, a quick intro into what BuildML is. So BuildML is essentially a community right now, primarily running on LinkedIn. We do weekly research hangouts like this. It's currently live. We also are going to start very soon monthly project builds, which is going to start next month. And we also have study groups so as to help folks brush up on their machine learning foundations. It's something that everyone needs from time to time. I myself need it from time to time, and that's going to launch on November. It's going to help you become a better data scientist as well as help you crack roles, specifically entry and mid roles. And all of this is in line with the mission of BuildML, which is primarily not just to land a role in data science or data related roles, but to build a long lasting and fulfilling career in data. So make sure you guys follow us on all of our handles on LinkedIn, on Instagram, and YouTube. We are going to be slowly start writing and sort of pumping out content, which is going to be mostly around a bit around research, a bit around landing your next role in data science, interview prep, a lot of those content. So make sure you do follow us on all of our social media handles. Now, quickly coming to the agenda. So what we are going to do today is we're going to essentially sort of go into how we actually read papers, which is sort of a multi-faced approach that a lot of folks at top universities use, a lot of folks at FANG uses. It's an approach that was, I think, came out like or popularized in like 2010s, primarily because research became a lot more industry relevant, and a lot more people wanted to know how to read, interpret, and use research. And that's when this sort of phased approach towards reading and reviewing papers came about or became popular. So we're going to start with that. Then we are going to break down the paper that we have in this phased approach, essentially starting by understanding what the problem and proposed solution is, then what the research space is, then what the approach and the results of the paper are, then sort of critically analyze the paper, and finally do a quick discussion between amongst ourselves, sort of what we liked about the paper, what we didn't particularly like, or what we could have improved with respect to that paper. Coming to how to sort of read papers. So typically, when you're reading papers, you don't sit in one shot and read the paper from start to beginning. You follow this sort of phased approach, where you initially start by trying to understand the problem and the proposed solution. Usually, I spent like one of my weekends, Saturday, Sunday, taking like 3 or 4 papers, figuring out what reading through essentially the abstract, introduction, and conclusion of those papers. Only those 3 sections, trying to figure out if this is a paper that I actually like reading, I find worth reading, and sort of making a call just based on those 3 sections, whether I'm going to read that paper or not. And what you're looking for, right, in these sections is A, does that problem actually interest you? And B, does that problem feel relevant to you in your day-to-day? So based on those 2 factors, you can essentially figure out if that's a paper that you want to read or not. So once maybe on a weekend Sunday, I read through like 10 of those introductions, abstracts, and conclusion sections, and figure out maybe like 2 papers that I want to read throughout the next week. So the next phase is to sort of understand what the research space in that particular paper looks like. For example, in recommender systems, we have quite a bit of research which actually started mostly towards early 2000s, or I would actually say, yeah, around early 2000s, even though there was work before that. Most of the sort of like seminal work, large scale work, etc., came around in the early 2000s. So what happened from there, how the current models are built on top of that the work that started in that space. So trying to understand that, that's going to take a bit of time. I recommend using like a huge amount of chat GPT or Claude. Both of them are fairly accurate when it comes to research, maybe 4 to 5 years in the past and then backwards. It's just the recent research that they get quite inaccurate on, but a research that's sort of a bit towards the past that they do pretty decent on. So use ChatGPT to understand the research space, primarily because when you're reading a paper, you will see this paper citing a prior paper. Don't immediately go and read that prior paper. Just sort of get a abstract understanding from ChatGPT so that you can understand how it's located in the research space and then move forward. The next is sort of to focus in on the approach and results of the current paper. What data sets did they use? What metrics are they using? And sort of what methodology in terms of how they're training, how they're optimizing, and how they're comparing whatever method they're proposing to what baseline methods they have. So make sure you focus in on those. Make sure it follows the base data science principles that we all use in our day-to-day. One of them that we'll see in this paper is sort of making sure you use a proper train, validation, and test set. And making sure you choose your hyperparameters on the validation. That's a basic principle. And we'll actually be diving slightly deeper into touching upon that at least later in this presentation. And finally, sort of critically analyze the paper. This is where you sort of figure out whether the benchmarks that they've used, the baselines that they've used, are actual standard benchmarks or baselines. The metrics that they're using, are they using some newfound metrics, or are they standard metrics that is used in the baseline? And then sort of figuring out what you liked in the paper and what you didn't like about the paper. Most often these papers are limited to 6 to 7 pages, so you won't get everything you want out of the paper. So it's good to figure out, okay, I didn't understand this section, or they didn't explain why this section is, which again is a good, we'll actually dive into that point a bit deeper in this presentation. So they didn't explain this section, that's quite common. So making sure you sort of make a mental note of those. And finally, figure out how this research applies to your day-to-day and sort of add it to your own sort of mind palace, mental map, etc. of the research space, so that when you read your next paper, you can build on top of what you already know. That's what we are hoping to achieve. And we'll show an example of all of this when we move through the session as well. And finally, obviously discussing it with peers so that you can sort of bounce ideas around and see what other people think of the paper. That's what Build ML Research Hangouts are for. So make sure you guys drop your questions if you have any in the drive. And folks who do drop their questions, I'll be sending out my notes that I made on the paper, which has a bit more information, a bit more context than I can provide in an hour session. So if you want those notes, make sure you drop some Q&As in the drive. It makes the session more interactive, and you'll get those notes as well. Coming to the problem and the solution that this particular paper covers. So we'll go into the research space in the immediate slide, but what this paper is trying to address is that a SOTA method that was released in 2017. This method was called Neural Collaborative Filtering, or NCF. It had a variant called NewMF as well. So it was a deep learning based deep learning recommendation systems approach. It was released in 2017. It sort of went on to be the SOTA in the space for a while, and it sort of inspired what is considered a go-to architecture nowadays called the two-tower architecture. Wouldn't say inspired, but they sort of came about at the same time. But yeah, people started noticing or became more familiar with the two-tower architecture, or the two-tower architecture sort of became more common in industry post this paper. So this was sort of considered SOTA, and a method that is used in this paper. This particular paper, a method that was used in this 2017 paper, this particular paper, they want to revisit it. They say that this method is sort of that particular design choice isn't backed by actual science. and the earlier work is sort of flawed in a certain manner. And what method they're trying to call into question is essentially in that particular network. This is the collaborative filtering architecture. Within that, what you do is essentially create a user embedding and an item embedding. So typically in recommended systems, what you want to do is you want to try and figure out if a user will use a particular item or not, or like a particular item or not. You can sort of depict it in either ways. So this SOTA architecture, also known as a two-tower architecture, how it starts is it sort of creates a user embedding vector using all the user attributes. User attributes can be demographic attributes, it can be what they liked, what they recently clicked on, a lot of such features. They essentially condense it into one embedding vector using some kind of neural network. It could be a feed-forward neural network, it could be a encoder layer, it could be anything. So they essentially condense it into an embedding vector. Similarly, the item latent vector is also created from item attributes. Item attributes could be anything like the genre of the item. It could be maybe if it's like a fashion, an e-commerce site that's dedicated just to fashion, like H&M. It could be sort of what type of clothing, color, the sort of like size guide, sort of sizes, any of those attributes. So whatever attributes you're using, it feeds into this and creates essentially an item embedding vector. And the idea, one of the design choices that they made was that once these embeddings are created, you can combine or figure out whether a user will use this item or not using a multi-layer perceptron or a simple essential. Essentially, you can think of as simple as a feed-forward neural network. So a multi-layer, you can use a multi-layer perceptron to combine these embedding matrices in such a way that whatever score you get, that will be the sort of like probability that the user will use this particular item. So going through this MLP, it will create a score. The higher the score, the more the chance the user is going to use this item. The lower the score, the less the chance the user is going to use this item. And this MLP, the usage of this particular MLP, is what this sort of paper calls into question. The authors, the original authors of the NCF paper, said that using the MLP, and because this multi-layer perceptron or this feed-forward neural network acts as a universal approximator, essentially meaning that if for folks who don't know, like a neural network is essentially can have multiple layers, and within those layers, the idea is that if you have enough layers and enough capacity, you can learn any mathematical function in the world, which is why the MLP is called a universal approximator. And the original authors of the NCF paper said that if we use an MLP or a universal approximator, it will be able to learn anything. And that is why they are using an MLP. And they showed that the use of the MLP is better than the use of any other method, especially something simple like dot product. Dot product being just, if you have two vectors, one being 1, 2, 3, the other being 2, 3, 4, you just do element-wise multiplication and sort of sum it up to get your score essentially. So they said that using an MLP has more power, is a universal approximator, and therefore a better choice than something as simple as a dot product. That is what the authors of NCF originally proposed in 2017. And they said that using such an architecture makes your system much more powerful and much more accurate. The paper that we're discussing today calls into question that essentially, does MLP make your system more accurate on in real world recommended systems or not? And I like this paper a lot, primarily because we'll dive into that a bit deeper in the session as well. But I like this paper a lot because it helps you sort of reassess. It helps you understand or makes you focus in on all the design decisions you are making in your architecture and how it can have an impact on the final performance outcome. And B, it sort of pulls the audience away from this current trend of uh, going to deep learning models as your first model. Deep learning models are indeed very powerful, and it's very uh, good to use them, especially in sort of domains like computer vision, and recently with text, it's been catching on fire. But you have to understand that deep learning models are models with immense power and ability to model almost extremely complicated functions. But to do so, you need a huge amount of data, and you need to control the parameters in in sort of very accurate ways, so that the model actually converges and gives you decent performance both on training and generalize as well as in onto your test as well. Whereas simpler models, especially like this method of using a dot product, is a much better way of building a model in a way that you get feedback immediately and you can improve your model continuously. Like deep learning is sort of in a ways like throwing a billion darts into a room where in some place in the room there's a dartboard, whereas using a simpler method like dot product, where you can sort of throw a dart at a board where you know where the board is, and you can sort of see where the dart lands, you get that feedback, and then you can adjust it the next time. So that's sort of how you should keep in mind that deep learning is. And hopefully this paper convinces, I mean, it at least convinced me, and hopefully you guys resonate with it, that DL should not be maybe your go-to model in any situation. I mean, like, not in every situation, at least. There are certain situations where you can start with it, but it shouldn't be the case in every situation. Now, quickly going through the recommendation systems space up until, I would say, even 2023. So it all started with content-based filtering systems. So content-based filtering systems use something as simple as user attributes to figure out what to recommend to you. For instance, the earliest content-based filtering system, just based upon where you were logging in, what your age, gender, sex, which they sort of collected initially in like a form, they would provide you recommendations. It could be something as simple as that. Collaborative filtering models, essentially, the core idea behind it is recommend items to this user which other users similar to this user have liked. That's the core idea behind it. There are a few different ways to go about it. There are these memory-based ways where you remember who the most similar user to a particular user is. And when you need to provide a recommendation, you call upon those similar users to figure out what to recommend to the user. And there are model-based ways where you break down users and items and sort of break them down into what we call latent or hidden embeddings, essentially deriving what the essence behind what makes a user, and deriving the essence behind what makes an item an item. And then whenever you need to provide a prediction for a particular user and a particular item, you combine these essences essentially to get to that score. That's what a model-based approach looks like. And within model-based approach, the most common one is what we call metrics factorization, where essentially you represent the user item as a metric, an interaction metrics. As an interaction metrics, essentially, where users are the rows, items are the columns, and the value in the interaction metrics essentially represents either the rating the user provided for the item, or whether the user has interacted with that item or not, in which case it's like a 1 or 0. So that's essentially how the metrics looks like. And the metrics factorization is a way of decomposing that matrix into smaller matrices. And if you decompose it and store those smaller matrices, whenever you need to get a particular user item rating or whether a user likes a particular item, you can just multiply those two matrices together. That's the core idea. It gets a bit more convoluted when you look at the math, but the core idea is you can just combine those two matrices back together that you got via matrix factorization. There are also deep learning methods like the one that we just discussed, like NCF, which we'll go a bit deeper into as well. But there's that deep learning approach of creating those or extracting the essence of a user and essence of an item, and then recombining it to get the recommendation for any user or any item. Hybrid methods are nothing but what combines content and collaborative filtering. You can use maybe when you initially start an e-commerce solution, you won't have a lot of interaction history, as in you won't have an idea whether essentially, since users are new to your platform, you have no idea what they have liked, and you have no idea for a new item who might actually like this item. It's called a cold start problem. So content-based filtering actually works pretty well for cold start. You can maybe use the IP of a user to figure out where they're coming in from and sort of recommend products based on what's popular in that region. That's a decent content-based filtering system to start with. But then later on, as you get interaction history for the user, you can switch to collaborative filtering. So that's one way of implementing hybrid methods. There are several ways. And I think I saw a question about what does sort of Netflix, YouTube use. The specific algorithm, obviously, is sort of a trade secret, but typically how they work is sort of in a staged approach. So usually they have this huge corpus, like let's say Netflix or YouTube has this huge video corpus, and they have a user history and content. User history being what videos they watched and what videos they watched throughout, what videos they dropped in between, stuff like that. So essentially what they liked and what they didn't like. So that's the data that they have, and how they move through this staged approach is first they do candidate generation, where they sort of figure out for each user item, for each, let's say, typically what they in the industry, what sort of accepted in currently is item based collaborative filtering, where for each item you find the most similar items. So let's say in candidate generation they're using item based collaborative filtering. They don't need to necessarily use, they could use something like 2 towers as well. But if they're using item based collaborative filtering, once a day they'll run it and they'll figure out for each item what are the maybe the 1,000 most common items, or in this based on this maybe a depiction, like 100 most common items, 100 200 most common items for a particular item. Then when throughout the day, when a user logs in, what they do is based on what the users is currently watching, what's maybe trending currently for that day, all those features they accept, and they re-rank those 100 to figure out what videos to sort of recommend to the user at any point in time during that day. So once a day they do candidate generation, just because it's so freaking huge. But at the end of candidate generation, for each item they might only have 100, so the size of the metrics drops from maybe like hundreds of millions cross hundreds of millions to hundreds cross hundreds. And then from that, they can sort of start providing rankings at a much faster level. And because the size of the search space, essentially, since it's reducing from 100 millions cross 100 millions to 100 cross 100, since the size of search space is decreasing, you can use more complicated or more resource intensive methods, which happen to be more performant as well, like 2 towers or something like that. So typically here they do, I mean, in the industry, they do use some form of matrix factorization, and here they might use something a bit more advanced like 2 towers. It again depends on what's working for them. Like places like Alibaba, they have mentioned that they have slowly started using something called graph neural networks as well, which is also something in the recommender space. For folks who are interested, I actually have links in my notes that cover a lot of these graph neural networks, wide and deep neural networks, 2 tower neural networks, stuff like that. So make sure to ask questions and drop them on the Excel, and you'll get those notes as well. So that's a basic idea of space, content, collaborative, hybrid methods. And in 2023, there is a lot of, not in 2023, but post 2015s, there is a lot of focus around deep learning model-based approaches for recommendation systems. So, and one of the ones that became popular, I think in 2017, was this neural collaborative filtering. Like I mentioned, it essentially condenses the user attributes into a dense user embedding, and condenses the item attributes into a dense item embedding, and then combines them in a multi-layer perceptron or a feed-forward neural network, or a simple sort of straightforward neural network, an easy way to remember it. New MF is another approach that the authors recommended in the same paper. It's very similar. Like, this is essentially the same as this NCF. It's just that they combine it with the normal matrix factorization. Normal matrix factorization, as in these two just go through an element-wise dot product. I mean, element-wise product is nothing but dot product, sorry. And the embedding that's sort of created post this, the value essentially that's created post this, and the value that's created post this, it's concatenated, and they go through a sigmoid to get the, a sigmoid to basically get the score at the end, and they compare it with what the target is. So it's essentially a variant, but the main focus for most of our conversation going forward is just going to be neural collaborative filtering. And neural collaborative filtering, again, create the user embedding, create the item embedding. Once that is done, these are called the neural CF layers. And what they're saying is, use an MLP. The MLP is a universal approximator. It has immense power. And because of its power, it's going to be more accurate than simple dot product. That is one of the main design choices made in the paper. And that is what the today's paper is going to call into question. Just quickly going over the question, what about Walmart? Yeah, won't be discussing, I guess, company-specific questions. What's the full form of GMF? Generalized matrix factorization. It's nothing but matrix factorization. They call it generalized just because they included a weight matrix within the formula, which allows it to learn certain parameters that make it sort of suitable for anything. But simple way of looking at it is, it's just matrix factorization. You can just think of matrix factorization. Yep. Yeah, weighted dot product, essentially. Yeah. Cool. Before going into the next section, which is the approach and the results, just a quick call out to our partner for today, Automate Apply. So like I mentioned, BuildML is not just here to sort of have these research hangouts, but we want to help folks build sort of like a long-lasting career within data science, and that initially starts by cracking a role into data science. And one of the hardest parts of that is, or one of the most horrible parts of that is the job applications portion, where every day you have to spend like an hour and a half going through multiple job boards, figuring out a job that matches your profile, and then applying to that particular job. So it not just takes 1.5 hours, but just because of how draining it is mentally, you're going to spend like another half an hour to 1 hour just recovering from it. And it's not time, I would say, very well spent, because it's a skill. It's not something that takes any actual skill, and it doesn't develop any skill over time. So that's where Automate Apply steps in. It essentially takes care of the job application process for you. It's about $1 for every 2 applications. So it's like 50% cheaper than everything else on the market. And for folks who are interested in checking it out, this is BuildML's link with respect to our partner. So you'll get, I think, around 10% off on the price. So do check it out if you are looking to transition into data science. It's going to save you a bunch of time. Now, coming back to our paper, specifically going into the approach and the results of how the authors proved that the neural collaborative filtering layers, essentially the use of a multi-layer perceptron as opposed to dot product may not be as good as the authors thought. Um, So how actually they proved this? They took the same data sets that the 2017 authors used, which is the movie lens 1 million data set and the Pinterest data sets. Both of those data sets, the 2017 NCF authors treated it as implicit data sets. So what is implicit? So in recommender systems, there are these two concepts of explicit and implicit. Explicit essentially means when a user actually leaves a rating for an item on a scale of 1 to 5 or 1 to 10, whatever. So that's called an explicit rating, where a user lets you know whether they like the item or not. Implicit is a bit different. Like when a user, for example, when we click on a video on YouTube, it doesn't necessarily mean we like the video or we don't like the video. We may even see the video in full. At times we may not be actually seeing the video. We might have stepped away. So just because we click the video, just because the video ran the full, does not mean we necessarily like the video. But it's somewhat a signal that's slightly different from they disliked the video or they didn't feel anything about the video. It's a somewhat maybe slightly positive signal. But it's hard to quantize that. It varies drastically from user to user based upon how they behave. So it is a signal. So what they do is they treat it as implicit signal, where they make a difference from if a user interacted with a video, they call it 1. If they didn't, they call it 0. It doesn't mean they like the video or they didn't like the video. It's just interacted, didn't interact. So 0, 1 binary values. So essentially movie lens and Pinterest, they essentially convert into this implicit data set. They being the original NCF authors. Our current days authors are just copying what the original NCF authors did with respect to the data sets, so that they can show that the NCF authors were flawed in their assumptions. So whatever the NCF authors did, they're replicating in terms of the data sets. In terms of metrics, again, they're using the same metrics the NCF authors used, which is hit ratio and NDCG. Hit ratio is essentially, let's say you have a data set where the user liked maybe or interacted with 20 items. You take 15 of those items and you're using that to build your model. 5 of those items you're not touching. So now when you're going to evaluate your model, you're going to see, you're going to essentially produce a probability score of whether a user likes an item or not for maybe 100 items. And you're going to rank all those probability scores. Now, if the 5 that we have kept outside come in the top 20 or top 10, we call that a hit. If they don't, we call that a miss. So that's essentially what the hit ratio measures. It measures how many of those held out items that the user actually interacted with. How many of them did we get in the top 10 or top 20? Because that's the only one recommendation set that the user is going to see on your website, and therefore that's the only thing that matters. NDCG is very similar to hit ratio. The only difference being in hit ratio, within the top 10, if those 5 held out came in the ranks 1, 2, 3, 4, 5, versus if they came in the ranks 5, 6, 7, 8, 5, 6, 7, 8, 9, 10, sorry, 6, 7, 8, 9, 10, it wouldn't matter. It would still be considered a hit. If they came in at the top 5 or the bottom 5, it would still be considered a hit. But in NDCG, the position, NDCG is normalized discounted cumulative gain. It's just a fancy way of saying that the position in the list also matters. So if the position is closer towards the top, you get a higher score, or the evaluation metric is higher. That's the only thing that you need to take away. So these were the 2 metrics the original NCF authors used, and that's the same metric that our current authors are going to be using. The only difference, they also use the same NCF and new MF methods that the original NCF authors used, and they set it up the same way that's described in the NCF paper. The only thing different that they're doing is that they're setting up a matrix factorization, the dot product, with L2 regularization and STD with negative sampling. So L2 regularization, I'm hoping everybody's familiar with it. It's just a simple regularization method that takes into account essentially outlier values, so that any of the features that may not be that relevant, their magnitude or their impact on the output essentially gets decreased. STD is simple stochastic gradient descent without batching. It takes one sample at a time. And why do they take one sample at a time? So that they can do this concept of negative sampling. So like I mentioned, in implicit data set, we know whether the user clicked on the item. If they clicked on the item, they might be interested in it. That we know for sure. But for instance, on YouTube, you have a billion videos. You click on maybe 100 videos a day. So those 100 we know the user liked. But what about the remaining 900 million, 999,999 videos? What about those? We don't know whether the user liked them. We don't know whether the user disliked them. So negative sampling essentially is, okay, those 100 that the user clicked, we know they are positive. So they have a value of 1. The rest 900 million, whatever, we don't know what in the movie lens data set is essentially 1 million. So whatever 900,000, within those, whatever has 0, you're gonna pick one of them randomly that the user didn't interact with, and you're gonna give it a value 0, and you're going to use it in your training. So when in STD, what we are going to do is we're going to take one positive sample, and randomly we are going to pick n negative samples. Typically that n is greater than 1, just because we don't know what's actually what the user doesn't actually like. So if we increase the value of n, the chances of finding something that the user doesn't like also increases. So that's why n is typically like 10 or 15, something like that. So one positive example and maybe 15 to 20 negative examples in each epoch essentially. So that's essentially how STD with negative sampling works, and that's the only sort of change that they made. And what they saw is that matrix factorization outperforms both NCF and UMF, the methods that were proposed in 2017 by the NCF authors. Metric factorization outperforms it, and also by quite a decent margin. Like in terms of like hit rate and NDCG, like um, these values are like considered pretty significant. Like once you worked on recommended systems, you will see like the performance you get is like fairly small. So these values are were pretty significant. Can be considered at least a statistically significant difference. And now that we know that metrics factorization or using a dot product is better than an MLP, we need to figure out why, what happened with the original SOTA papers in 2017, the original NCF papers. So one, in recommendation systems in general, it's very hard to set up and tune the baselines, just because a lot of people cut the data in multiple different ways, and sort of select or cherry pick whatever works for them in a lot of different ways. It's hard to really replicate research results, and it's hard to set up baselines when you're trying to improve upon those baselines. So that could be one of the reasons why the authors messed up and thought that MLP was sort of better than a simple dot product. But more likely, the result is because of improper regularization. The way they described generalized metrics factorization, simplest way to put it forward, is sort of like a weighted dot product. What they did was that the weighted part of that dot product, they didn't include in the regularization. So what happens is the metrics factorization that the NCF authors used, it was actually overfitting to their training set, because of which they got very poor performance on the test set. And you can actually see that because in the original paper, as the dimension size increases, dimension size being, like I mentioned, we condense the user attributes to a user embedding vector. This embedding vector can have a dimension between maybe something like 12. I mean, it can be as simple as like something as 16 to something as big as like 128. So this dimension size, as this dimension size increased, the MLP started performing worse, which is usually a sign that somewhere along the way you might have been overfitting. Sorry, not the MLP, the dot product started performing worse, or the generalized matrix factorization approach started performing worse, which is which is not maybe a strong signal, but a fairly decent signal that you might be overfitting to the problem, or your regularization isn't working as expected. But essentially, again, a sort of slight mistake in the mathematical formulation, which these authors have called out. Like I myself, when the paper came out, I did read the paper. I thought it was seminal work. I was also using like 2 towers quite frequently. It's not until this the authors of the current paper that we're seeing today, and other authors came out and showed that there is a flaw in the mathematical formulation, that people started noticing it. So yeah, this is a sort of like a good call out on how important a regularization is, and how easy it is to sort of maybe overfit to your training set and get like poor generalization results. And also one thing that a common thing that I think a lot of people picked up on, the original NCF authors, they did sort of cherry pick their results, in the sense that they didn't have a validation data set. So the parameters that they picked for their NCF and UMF models were sort of the best parameters on their test set. So that was sort of cherry picked, and a lot of people did pick up on that fairly quickly. But the regularization, in my opinion, again, would be like the main culprit of why they felt that the MLP, the universal approximator, or the simple feed-forward neural network is better than dot product. The regularization, again, is in my opinion, would be like the a main culprit. Another thing that the paper also pointed out was that the multi-layer perceptron, or MLP, even though theoretically it is a universal approximator, for most practical settings, it doesn't act that way. So just because it is theoretically, we as data scientists shouldn't consider it or treat it that way in actual practical settings. And how they proved it is basically they created like a bunch of pairs of embeddings. They calculated their similarity using dot product, and they tried to see if MLP could approximate a dot product. So they essentially trained it to predict the same score a dot product would. And they showcased that a huge amount of data, sort of like a impractical amount of data for most of us applied data scientists. An impractical amount of data is required for MLP to learn the simple dot product formulation, which is nothing but element-wise multiplication. And in addition, using MLP has other issues. One, which we'll also dig a bit deeper into the analysis portion. But yeah, the two sort of like main takeaways that we need to sort of like focus in on: one, definitely don't treat MLP, or essentially any deep learning neural network, as a universal approximator, because there does seem to be a trend where most of us sort of jump to a DL solution right at the go, hoping that just because the model has a lot of capacity to learn, whatever whatever the underlying function, this problem function, which could be a solution to this problem, this model will learn. But that shouldn't be the approach, and that's sort of like beautifully called out in this paper, in my opinion. That's the first thing to remember. And the second thing to remember is sort of specific to the domain of recommender systems, that yes, a two-tower architecture is still a seminal architecture, but the method of combining the embeddings at the final portion using an MLP here, that might be overkill. It's impractical because most people don't have that much data / compute to make MLP act as universal approximator. So dot product is better for combining embeddings in recommender systems. So those are the two key takeaways. One, generally don't treat MLP as a universal approximator. Two, in context of recommender systems, for combining embeddings, dot product works better or than at least for at least most uh, more complicated neural methods, dot products work better than most of them. And results for the dot product. Can MLP approximate a dot product? They ran it across multiple different dimensions, and each time the difference between what the dot product predicts as similarity, or dot product calculates as similarity, and what MLP predicts is the difference is pretty high. This line represents a statistically significant difference, and the difference is almost always higher for any kind of like dimension size. The other problem that I mentioned about MLP is the inference time. MLP has like a quadratic time complexity in terms of inference, essentially meaning that as the dimension of the embeddings, dimension of the user and item embeddings we discussed here, as their dimension increases, the time complexity increases in quadratic terms. But for dot product, it's linear. It's not just linear. There are a few approximation algorithms that make it sort of sublinear as well. So dot product essentially is like much faster. Now coming to sort of before maybe critical analysis, just quickly checking in on the chat and the drive for any questions. How do we calculate space-time complexity for DL algos? DL algos, it depends upon the number of heads or neurons you have in each layer and the number of layers you have. Typically, most layers you would use some kind of ReLU or sigmoid function. In all of that is essentially a dot product with a function on top of it. So most of that is sublinear. So you just need to see how many heads you have and how many layers you have, and multiply those, and that's sort of going to be your time complexity for DL algorithms, for most simple DL algorithms. If you're looking at like a transformer or something, that's gonna get a slightly more complicated, and I don't think I know how to calculate the time complexity of a transformer, but it's a good question. I'll make a point of it, and maybe after the session, drop a DM to me on my topmate. I'll just link it on chat, and I can hopefully get back to you with an answer. Sorry, not that one. Spelling mistake. Yeah. So time complexity of transformers, I'm not actually sure actually. Yeah, but yeah, simple neural networks. If it's like a simple ReLU sigmoid function, feed-forward neural networks, it's usually dependent on just the number of heads or neurons you have in each layer and the number of layers you have. The rest, it sort of depends. Yeah. Quickly going through the Excel as well. Are there any ways of addressing cold start problem other than content-based filtering? Yes. Like I mentioned, in user embedding matrices, the user embeddings that we talked about earlier, the attributes that you can have all the attributes and you can create a user embedding, or you can leave a lot of them as null or give like default values and create a user embedding as well. So you could still use this approach, which isn't like content-based filtering. It's a collaborative filtering approach. It's just that you're creating embedding from a less or a more sparse initial vector. Your performance might be slightly lower, but your performance would be lower even with like content-based filtering method as well. But yeah, you can use like if you have like embedding layers in your initial portion of your collaborative filtering, like if that's how your collaborative filtering is built out, like in 2 towers, you can combat that to a certain extent, like user cold start and item cold start. Talking about similarity models, what kind of vectorization methods have been chosen to facilitate this, and how does this affect the similarity methods? Didn't quite understand the question. So vectorization methods, in terms of like how dot product is actually done, or didn't quite understand that. If you could provide a bit more context, that would be good. So paper focuses on hit ratio and NDCG as evaluation metrics. What metrics you prefer, if any, and why? NDCG and hit ratio are pretty good metrics. I usually prefer precision at K, rate call at K, average mean precision at K. Those are the ones that I like in terms of performance. Then there are a few diversity metrics. Essentially, you want to make sure that the recommendations that you provide for different users are different, and you don't want to provide, like, sometimes just because of this thing called popularity bias in recommended systems, where a lot of people like the most popular things a lot. Like if a Marvel movie comes out on Netflix, a lot of people will like it. So what will end up happening is that that Marvel movie would be recommended to everybody on Netflix. So that's called a popularity bias. But maybe some people don't like Marvel, or they don't like movies like that. So you don't want to provide that recommendation there. So that's when you want to check certain metrics like diversity. Are the recommendations you provide for different users somewhat different, at least? So then there are those diversity metrics, and there are certain bias matrices as well. I have a link to the different types of matrices on my notes. So since you asked the question, you'll definitely get a link to the notes, and you can check that out. What are the common metrics in evaluating recommended systems? Again, we went through some, like hit ratio and NDCG, precision at K, recall at K, mean average precision at K. These are like other matrices. And like I mentioned, diversity, bias, there are a few matrices. You'll get them in the notes, link to a couple more in the notes as well. For rec use cases involving a description of certain items, example, courses, items, movies, etc., can similarity between descriptions be used to recommend items? Yeah. So in those cases, the description itself, you will break down to like a text embedding, and that text embedding you can attach or concatenate with your item embedding latent vector. I mean, you need to normalize everything so that they are on the same scale, but you can, like the text embedding, you can concatenate on top, so that it sort of represents a particular attribute of your particular item, like product description, course description, movie description, stuff like that. So yeah, that's definitely done. The similarity scores can then be multiplied to the value indicating user rating, user item description instead of genres, keywords. Yeah, definitely. You can definitely do that. That's a good point. Cool. I think those are pretty much all the questions I can see thus far. For sure. Yeah, the notes will be sent to almost everybody. I mean, almost everybody on call today, I think. Yeah. At least because I think everybody asked questions. So yeah, the notes will be sent. When I upload the YouTube video, I'll link the notes on the description as well. Cool. Coming to critically analyzing the paper. So yeah, this is the section where we sort of go through the paper and figure out, or sort of like nitpick and figure out what could have been better, or is this actually seminal work? So the first thing we need to check is the baselines they have used and the metrics they have used. Are they actually legit metrics in recommended systems? Yes, movie lens is a very popular baseline in recommended systems. So definitely legit. Pinterest is also very popular. The metrics they have used, NDCG and hit ratio, yes, very standard metrics for evaluating the performance of a recommended system. There are other metrics, like I mentioned, but here we are focusing only on performance. So those are standard metrics. The next thing about the paper, what we liked about the paper, or what we want to carry forward in sort of like our daily lives as applied scientists. We showed that a huge amount of samples, the current paper authors showed that a huge amount of samples is required for MLP to actually act as a universal approximator. So even though theoretically it's called a universal approximator in most of like DL literature, we shouldn't treat it as such. Like applied scientists as such, as us who are sort of working day to day, we should always be mindful that deep learning is a very complex optimization problem, and more often than not, we don't have enough data to find the global minima for that particular optimization problem. And this equation essentially just is a representation of how many samples you need. So depending upon the dimension size, you need an exponential number of samples. So if you have a dimension size of 128 and There's this thing called epsilon, which is nothing but an your error rate. It's usually around 0.01 ranges. It depends upon the problem slightly. But essentially, the main takeaway you need to have is um, you need a huge number of samples for MLP and DL in general to work as universal approximators. So even though theory calls it universal approximators, applied data scientists shouldn't treat it as such. And if we can, we should always start with simpler models where we can as sort of understand how the model works, get feedback, and improve the model. Whereas in DL, it's very hard to understand how the model works, get feedback, and improve the model. So start with simpler models first. Even on DL, start with a few layers first, and then slowly hit the larger models. One thing I didn't particularly like about the paper, and it's sort of a theme in deep learning research in general. They say that the dot product is a powerful embedding combiner. Like, we understand why dot product is a very good similarity function that can be mathematically proven. But they use that knowledge to say that dot product is a powerful embedding combiner, in the sense that if you use dot product in this initial model to combine the user embedding and the item latent embedding, that is going to be much more effective than using a neural network or an MLP or any kind of other function. They're saying it's a powerful embedding combiner, and they show it mathematically and they show it empirically, but they don't explain why it acts as a why dot product works this way. Why does this turn out to be such a good way of combining embeddings? They do sort of generalize and show that in most neural networks towards the end, in one way or form, we use a dot product. Like within sigmoid, there is actually a dot product. Within the softmax, there is a dot product. So we are always using towards the end a dot product. We have always used that historically, and that's been the most effective way of getting probability for a binary class. Like if you're using sigmoid, or for multi-class, you're using softmax, and it's been very effective historically. But why it proves to be that effective, why does it seem to be this good of an embedding combiner? The paper doesn't really provide a strong intuition based explanation for it, or a mathematical based explanation for it. So yeah, that's something that we can definitely, like, as we read papers, if there are papers that propose that they can help provide explanation for this, those are definitely papers, in my opinion, to go out and read. And it's sort of a good thing for us as applied data scientists to keep our eye on, because that understanding might help push the field forward as well. So yeah, those are the main critical analysis that we have. Now, I think we are about at time. And I think most of the questions that we've had, we went through them as well. Sort of like quick clean up the notes. Most of the folks at least asked questions, and I feel like the session was fairly interactive, with some questions coming in via the chat as well. So I'll actually post the notes at the end of the description in the YouTube video, which will be up in a week or so. For folks that already don't know, we have our socials that are slowly building up. We'll be having all the recordings on those socials, as well as on YouTube and Instagram. We'll be posting sort of at least weekly content to help you stay up to date on ML. Make sure that you brush up on your foundations of ML, make sure to help you prep for your upcoming interviews, stuff like that. So make sure you follow and subscribe to our particular socials. And again, just to help everyone on call here today build out your own networks, if you make a post stating 2 takeaways that you had from today's session and tag me and BuildML, I'll make sure to both like and comment on those posts, so that you get more visibility on LinkedIn. This is just you're just going to make a post about research. It's not job related, so don't be afraid. Like in case you're worried about, oh, my team is going to see it or my manager is going to see it. It's not job related. BuildML is more focused on research. So yeah, feel free to make a post. I'll I'll be liking it, BuildML will be liking it, and we'll be commenting on it. So hopefully you guys will get more visibility on LinkedIn as well, help grow your networks as well. So yeah, next week we won't be having a research hangout. I'll be actually traveling. So the week after is going to be when we are going to be doing the next research hangout. Within the upcoming few days, we are going to be releasing what paper we're going to be doing for that hangout. So make sure to stay tuned to my LinkedIn. I'll link it on chat as well. So make sure you stay tuned on my LinkedIn as well as BuildML LinkedIn, so that you know what the next paper is and you can sort of get started reading on it. And yeah, hopefully see you guys for the next session. Thanks everyone. I'll stay around for a few more minutes just in case anybody has any questions.